is a picture of Cambridge, UK. I don't know, does anyone know who might have been the first person to describe the quantum Zener effect? The quantum Zener effect. Yeah, it was actually occurred in a letter correspondence between two persons quite a long time before that.
Actually, Yakir has an earlier version of quantum Zener effect. You better ask him tomorrow.
No, maybe it was,
he never published it.
There's a version from the 40s where someone described the quantum Zener effect. It's not his focus is that there was Alan Turing who took a course on quantum mechanics in Cambridge and then looked at unitary evolutions and wrote a letter to a friend that if you would do continuous measurements at this frequency, you're going to face the state, and it's not kind of all. So that's just a bit of trivia before we get going. Thanks. So I'll start with an outline talk. So I'm going to talk about this thing called interaction-free communication or counterfactual-communication, as it's also known. This is kind of a protocol that builds on the Elitzur-Vaidman bomb tester. And as with many of these interferometers, when you're thinking about kind of paradoxical things about them, we often talk about where or where not the particle was. But according to some interpretations, quantum mechanics, you can or cannot do that. So I'm going to present my own take of how one might go about thinking about where a particle has been in between oscillations of it. And then when I've done that, I'm going to go back to these interaction-free communication protocols or counterfactual communication protocols and think about, according to my measure, where was the particle in these things. And this is kind of largely, some of it's published work, a lot of it's not, but it's things that I've been thinking about on and off for a couple of years and discussing with Crispin Barnes in Cambridge and Irati Alonso in Vienna. So let's get going. I'm going to start by just briefly introducing this interaction-free communication and counterfactual communication. But maybe just let's do a raise hands. Who in the room has heard of or knows what interaction-free communication is? Yes, this is a majority, but not by much. So let's still kind of go through the basic idea. So the basic idea is that you have two parties out involved, but wish to communicate with one another. And Bob wants to send a message to Alice. And the normal way Bob would do this is by encoding his message in some particles or waves and sending them to Alice. So I'm communicating with you guys now by sending sound waves to you. If I send you a letter, the particles of the letter will carry the message to you. And in interaction-free communication, the idea is to cut out the transfer of particles and waves from Bob to Alice, but still send the message from Bob to Alice. So this is what we're going to see if this is possible. The protocol is going to build on the Elitzur-Vaidman bomb tester. Just looking at the standard setup, you could kind of see that there is something, this sort of maybe interaction-free communication going on. If you thought of Alice as sitting by detector D1 and D2, and then Bob was sitting around the bomb, so B stands for both bomb and Bob here. If Bob would put in the bomb, he would change the kind of detection output that Alice's detectors, but since he's blocking all the wave function that goes here, it would be hard to claim that in the case where D1 or D2 takes a particle loss in its lab. So it seems like if he puts in a bomb, in an interaction-free manner, he can change the stuff. But if he wants to transmit another bit and not put in his bomb, and he leaves it outside, then we see the sound wave function goes through his laboratory. So it would be hard to argue that this bit happened in an interaction-free manner. And so here, particles seem to flow from volatiles. So let's see if we can do better than that. So I think all with friends have this concatenated version of the Mach-Zehnder interferometer, where instead of using 50-50 beam splitters, you use these beam splitters that have their reflection transmission coefficient set by some integer number n, which is the number of beam splitters. And by doing that, if you send in a single photon with no bonds in the upper half, you're going to coherently evolve into detector 2. And if you have bonds in here, you're going to simulate a state and stay in the lower half. So this is kind of, it's the same as before, you're just eliminating the kind of erroneous events. And this is the basic building block of the first suggestions for counterfactual communication. So the idea was to take one of these guys and then make it much bigger. And then make many copies of concatenated Mach-Zehnder interferometers and stick each of these copies into one of the arms of the bigger one. And then I have a picture of that here. So what we see here is like these green things are mirrors, and these are beam splitters. And these central beam splitters, they form a huge concatenated Mach-Zehnder interferometer. And in between each couple of mirrors and the big one, you have another concatenated Mach-Zehnder interferometer. And they're big N numbers of outer beam splitters, and then they're big M numbers of beam splitters within each concatenated Mach-Zehnder interferometer. So now the idea is to use this in order to communicate. So you can allocate Alice lab to the lower part of this thing, and then Bob's lab, he's just sitting in the complete upper part of it. And then there's some transmission channel in between them. Let's look at what happens in this interferometer. So the photon comes in from Alice's laboratory, and a tiny bit of wave function kind of leads through to the inner concatenated Mach-Zehnder interferometer. And if Bob's laboratory is free, so there are no bonds here, then that tiny bit of wave function is going to coherently evolve into the upper state there, where it's stored by detector D3. And then you get the kind of Zeno effect, because only small amounts of wave function leak up at each outer beam splitter. So you're Zenoing your state to stay in the lower half. Similarly, if Bob now puts in detectors in his laboratory, after the first beam splitter, a tiny bit of wave function leaks in here, and now it's Zeno by these inner detectors into the middle state. And then it reflects back and interacts with the original beam coherently and constructively towards the middle path. So a tiny bit more of wave function leads through. And as you go through the device, your state will evolve coherently between the lower and the middle path, while it's being Zenoed from the upper path, so that you end up at detector D2. So this is the kind of idea. Bob has a choice to put in a detector and not put in a detector. And depending on his choice, Alice gets a tick at D1 or D2. So these are the two logic bits that Bob might wish to transmit. And the question now is this interaction-free communication. Did the message go from Bob's laboratory to Alice's laboratory without being carried by any particles? And in this scenario here, even someone who likes the Copenhagen interpretation would probably say that the detector E2 ticked without any particles going from Bob to Alice, because Bob is continuously monitoring his laboratory and he never finds any particles. So this logic 1 scenario, when the detector E2 ticks, is not that controversial. The interesting thing is the logic 0, where Bob is not continuously monitoring his laboratory. He only monitors it after each concatenated Mach-Zehnder interferometer. And Vaidman was the first one to kind of realize that there might be something fishy going on here. So this is what I like to study using some information-theoretic techniques. So we study these within the two-state vector formalism and with weak values and things like this with a different take on it. So in order to do that, I need my own kind of idea of where a particle was when no one was looking. So I took this is a quote on Wikipedia on the Copenhagen interpretation. So Wikipedia says that within the Copenhagen interpretation, no truth can be attributed to an object except according to the results of its measurement. So, you know, if you're a Copenhagenist, it's tricky to talk about the past half of a quantum particle unless you're measuring it. But I don't know if, you know, how many people here are happy with the Copenhagen interpretation. Okay, John. So John, you can just, you know, go for break now because you're not going to like the rest of this talk. So I'm just going to, as much of the diplomatic way as possible, try to kind of say something beyond this and see if we can't really talk about the possible of the quantum particle. But I'm going to start classically. So first I want kind of a definition of what the particle is, and I want my inspiration in classical physics. So a few years ago, I spent a bunch of time in Oxford, UK, speaking with one of their philosophers, Peter Dewey, who specializes in kind of, you know, classical objects and stuff like this. And he told me that the way that classical philosophers usually think about a space that's occupied versus a space that's unoccupied is, can you store information in the space or can you not? So I know that people like there's some fewer people that don't like this definition and say, you know, you can store information in vacuum in certain ways, things like this, but I'm gonna stick with this definition for this talk. So I'm gonna say that, you know, a regional space is occupied by an object if you can encode information in that region of space. And the thing you encode the information in is an object, which is different to vacuum, which you cannot encode information in. So here I have one box with a particle inside it. And, you know, I could change the temperature of this particle, I could color it, I could change its angular momentum, or if it was a quantum particle, I could change its polarization of this photon. So these are all examples of you know, how you could encode information into an object. And throughout this talk, information will be denoted by this I, and the thing that I've encoded will be denoted by theta. So here's an example now. It's a simple example. I have an object, a classical object, that can take one of two paths. And then after these two paths, I'm going to detect it. But I'm not going to monitor it when it goes through these two paths. I'm going to look away. And then in these two parts, there are certain places where information could get encoded into the particle. So if I come back later when the particle has evolved, I could look at the particle and see, what information is encoded in it. And if I would find that information about theta 1, theta 2 to theta 6 is encoded in the object, but not information about the other parameters, I would say that the particle took the lower path. So this is kind of the framework that I'd like to extend different.
I'm just having a little bit of trouble with the definition, which sounded okay when you said it.
Okay.
But on the other hand, when you talk about encoding information, you necessarily mean that you're talking about a system that could be in one of at least two different states.
Yes.
But now you're saying, is there a particle there or not? You're kind of acting as though there's one state, or at least you're assuming the answer to that question is the same in both of the states. Whereas obviously one way I can store information is by using no particle to represent a 0 and one particle to represent a 1. So I'm just curious, how you're making sure something is held constant while something else can vary in the context of that definition.
Yeah, I think this is a good question. And I think, so basically, in this setup, I say that I know that there's one particle. And then if I want to know where did that particle go, when I look at it, I will look and think, where was information encoded into it? So in this specific example, I've said that there are two pods and one particle. I know that. When I measure it, where does information come from?
I don't know if you like interventions.
Sure.
But if you have a promise that you know that there is one particle, you don't need any quantum, nothing.
No,
they want to choose one box, it's not there, you find that it's there in interaction manner.
Yeah. And indeed, this is totally a classical thing. So this is just, if you agree with that, I'm happy. Yes.
Yeah, quick clarification, because you define information as being the thing that has to have a particle to store it. But here you have locations in space that the particle is going to interact with and then gain the information from the location in space. Does that mean there are particles in each of these boxes that it has to interact with one by one to get the information out of the particles, storing the information at that location?
So I think I define the empty space as something where you can't encode information.
Right. So these theta 1 and theta 1 prime can't exist in empty space.
So you could, attempt to store information there, but you would fail in empty space. But if there's a particle there, you will succeed.
This is my question. Are you assuming there are particles in each of these positions? That these thetas actually come from some detector particle there?
No, I'm assuming that, at each of these thetas there stands a guy who tries to paintbrush something that comes through.
He's a part of this information.
Yeah, but
So there is a detector there that's interacting with the particle.
yeah,
Okay.
yeah.
That's okay.
And if I want to know where this particle was, I will go and see, where this information goes.
But then there was a little bit of a leap. It's not that you're asking whether or not information can be encoded in each of these regions, because you always have that God, there is information in both regions. You're asking whether the information can be extracted from that region by this other particle.
Yeah, okay.
Yeah. I just wanted to make
That's yeah. So a particle was for information wasn't encoded. Are people happy with that? So I want to use this to just go to quantum stuff and talk about where was the quantum particle. I need on the flight yesterday I decided that I would probably be jet lagged today and I'm the last speaker of the day, so I cut all my kind of technical slides. So I'll just give you a brief summary. I'm sure you appreciate this and go through some of the derivations. Here's my quantum experiment for encoding information into a quantum particle. So I have like some quantum particle, and today I'm going to do everything with pure states. This slide. And if I want to encode information about something, beta, I do that with unitary transformation. And then I end up with state side beta, but now it depends on this quantity beta that I wanted to encode in it. And if you measure many copies inside, you could learn what beta was. So the output of this experiment, is a state of beta that depends on this thing I've encoded in it. And how do you quantify the amount of information that's encoded in it? It's quantified by this one here, the quantifying information defined by Arvidsson and Case in the 90s. And just, I'm not going to go through the derivation of that, but like, why does it matter? Well, you would, if you measure many of these states, you would say that these states have a lot of information about beta. If someone who didn't know what beta was to try to estimate it, would be able to do so with small variance. And in the number of many trials, the variance of guessing what the parameter is if you don't know it, scales as one of its quantification information. So it's just a way of quantifying how much information these states carry about these parameters.
Does it kind of matter in terms of encoding? Most of the examples you've given, the guy with the paintbrush or changing the polarization, are all local. But you could also change something where you're changing a relative phase relative to another thing, and then it's an intrinsically non-local encoding of the information. And I feel like that's gonna be tricky if we're then trying to use that as a way of saying where the particle is.
Yeah, okay, I agree. So I'm gonna try to be local here.
Okay.
For this, so I agree. That would be fine.
But if intervention is local, this is enough.
Okay. So I need one more assumption. It's the same, it's the first assumption of this earlier today, which is that I'm going to say that if I'm doing an experiment with one photon, and there's only one path it can take to the detector, then the particle, it must have been on that path from emission to detection. So now I want to check just to kind of be able to benchmark all the other parameters I'm going to look at according to how much information could be encoded in that one particle. So if you're going to compare different parameters, you're definitely going to use the same kind of encoding mechanism. Otherwise, it's be hard. This is all told us a second ago. So I'm going to assume that my interferometers today, they don't care about polarization, and I'm going to encode information and polarization, but we could do it in different ways. So in this scenario here, of course, we rotate the polarization, the state will set this afterwards, and the way I set things up is such that this state carries one unit of Fisher information. So that's how much information you can encode and say goes through this direction. Sometimes people will say that if you kind of nudge it or encode some information in it, that's going to disturb the state. And that's certainly true with many interferometers. So if the Fisher information depends on the parameter data, or if the interferometer does, I'm going to be assuming that the parameter that I encode is equal to 0, or is infinitesimally strong. So I'm always going to assume that these encodings are encoding very, very weak parameters. Of course, if you have the opportunity to rotate the polarization and you choose not to, that's also encoding information. It's just that it's the information that you chose not to. So let's look at these simple examples. Let's start with just the beam splitter. So if I send in a horizontal photon here, and then I'm going to look how much information I could encode in it in the upper and lower half. And so I'm going to kind of take the wave function that comes out here and see how much information could have encoded in the upper and lower half. Does anyone want to venture a guess of how much I could have done with the theta 1 and theta 2?
One each, and maybe if you need to take your V-splitter fraction into account.
Yeah, exactly. So this is the 50-50 beam split there. And this is the output state, and I get a half and half. Because, when it just went through, I got 1. So this is counterintuitive, right? And this would correspond to thinking about this experiment in following way. So, Alice, she kind of controls the whole thing. She controls the input and the 2 detectors, and she just thinks of this whole experiment as involving the same type of particle every time. You could also think about it as, Alice just sits here. She knows how the setup looks, and she could potentially even have notes where she tunes theta 1 and theta 2. And then she wants to know, how much information post-vector on the particle coming down here can I get about theta 1 and theta 2.
Theta 1 and theta 2 or theta 2?
She sits here.
Yes.
She wants to know how much information can she get about theta 1 and theta 2. So if you calculate the fission information, she gets 0 information about theta 1, and now 1 unit of information about theta 2. And this is, of course, post-vector of only the vector in this case. I think this also kind of makes sense. Now let's go to the Mach-Zehnder interpretation. So again, I send in horizontally polarizing the photon. I look at the wave function that comes up in Mach-Zehnder interferometer, and I want to know how much information could have been encoded at theta 1 and theta 2. Anyone? I should guess.
Are you allowed to use path information at the end, so you actually have basically 2 qubits to study instead of 1?
So
only doing a polarization.
In this scenario, you will have both polarization and path information. Because you're going to put, so the optimal measurement to do of the Mach-Zehnder state is to put the detector here and the detector there that both measure polarization and photon patterns. Of course, because it's balanced Mach-Zehnder interferometer, you only ever detect things in the upper half
If they don't want to just
or if it goes 0, which I said I would let you know.
So she told me that she they were the angle of the half index, which is rotating the polarization state.
Yeah, they want to do polarization.
If you get it, all else, you don't get the difference.
Yeah, so but I'm after how much information about theta 1 and theta 2 will I be able to get at the outputs here?
I would guess 1 bit for each.
Yeah, almost. So you get half unit of fission information per each. And again, it's a single photon that goes into a 50-50 beam splitter. So kind of half of the photon goes through theta 2 and half goes through theta 1. And that's how that works.
Is that specific to your assumption that theta 1 and theta 2 were small? Because it's certainly conceivable to me that since at the end you can get 2 classical bits from a readout instead of 1, you might eventually get 2 units of Fisher information, which is not in this regime.
No.
No, it never happens.
Not in this setup. So irrespectively of the value of theta 1 and theta 2 here, if you do the optimal measurement at the end, you're always going to get half a unit of Fisher information about theta 1 and theta 2.
So let me give you my counter argument, although you've actually worked this out.
Yes, I think this is
the polarization detections. Right, I really have 4 different detectors here. We haven't thrown it that way. I learned something about theta 1 or theta 2, but just looking at which path I come out, I learned something about theta 1 minus theta 2. So it seems to me I'm simultaneously, you see what I'm doing. But that still leaves you with exactly 1 total unit of Fisher information.
From my point of view, this comment says that Fisher information is not a good thing to use.
So maybe, yeah. We'll see. So the final thing to look at is again Mach-Zehnder interferometer. The left beam splitter is 50-51. The right one is I'm now going to change that so it has the variable kind of reflection and transition. And I'm going to do one more thing. I'm now going to postulate only detecting the particles at P1. And then ask, postulating on these detections, how much information will I have about theta 1 and theta 2?
Now, do I get to say one in each?
Yeah, you get, but unfortunately, so now things are much more complicated. So now you get something, I'm going to plot these things. So this is your information about theta 1, and this is about theta 2. And then if I plot these guys, it's small, but it says information up there, and then the phi, which is the coefficient that determines the reflection and transmission of your beam splitter. So depending on what that phi value is, you will get values of the Fisher information that can long surpass 1 unit. So this is similar to anomalous peak values. By postulating on rare events, which happen if phi is close to pi over 2, your state becomes more and more sensitive to nudges of theta 1 and theta 2. And if you do these experiments and you try, so if Alice sits there and she tries to learn theta 1 and theta 2, she doesn't know what they are. If phi is close to pi over 2, she will learn as much in absorbing 1 photon as you would in absorbing maybe 100 that just went through polarization rotation. So this is something that some people call superpresence, which is post-vector on certain outcomes. It can appear as if the particle went through the same polarization rotator 100 times. So this was the last kind of part that I wanted to share with you on this measure before. Just to summarize.
David,
Yeah.
so often when we talk about Fisher information and weak values, what we find out is that even if you have rare events, what we find out is that all of the Fisher information goes into that rare event, and there's also in the other one, but it's still like a conservation of Fisher information. We don't get more information; it's just all goes into that rare event. But here you're actually saying that the Fisher information.
No, I'm saying exactly what you're saying. So I'm postulating only on outcomes here. So, say that if Alice was both a B1 and B2, and she waited until she had detected 100 photons, then on average she would get half a unit of Fisher information from these guys. But if Alice sits down here and waits until she detected 100 photons, she's going to have to wait way longer because most of them end up here if she doesn't detect them. But after she's detected 100 photons here, then those will have carried a huge amount of information.
I see.
So there's no free lunch. Like you're kind of the price to pay is that you don't detect with that whole. So here's a summary. So if you don't do any post-selection, you just look at the states that come out. You kind of get the intuitive thing, at least for these interferometers. But if you do post-select, then you can get these anomalous things where things seem to have been very present somewhere. Yeah.
Very much like weak values of projection operator.
Yeah. Very much like that. I don't know, you can, I think one thing, and often when people talk about weak values, a criticism that people give is that when you're doing the weak measurement, you're actually nudging the state, right? So you're kind of, fiddling with the interferometer. Here you can make theta 1 and theta 2 sharply 0 and say, I want to encode the information that theta 2 and theta 1 are 0, and you still get this effect. So you're not changing the output statistics of your detectors in any way. There's some differences. So I think if you do the weak value stuff, I have not done the calculation, but I would assume that these two quantities there will be the same, which they're not if you look at how much information you encode. So there's some differences. I don't know all of them. And Justin?
Just curious, if you multiply those by that post-election probability, do they end up like half and half, but then skewed, or?
Yeah, they become all half.
There's a paper of my student at Elitzur-Vaidman, which kind of really make analysis of this.
So I know wanted to use this to kind of talk about interferometer communication, but I almost used up my time. I think I got a lot of questions, but I'll just keep going for like 10 minutes, and then I get as far as I get. Let's see. So this was what we wanted to analyze. It's kind of tricky to analyze. So, we have a paper where we've analyzed it, but just for now, maybe let's go to Lev's nested interferometer instead, which is very similar to this big guy here that I showed. So this thing fails sometime. So again, if Bob wants to send a message to Alice without sending any particles to her, we could think about this interferometer. This beam splitter lets through 2/3 of the wave function and reflects 1/3. This one is also 1/3, 2/3. And then these two are 50-50 beam splitters. And then Bob can move the detector in and out here, and he's going to do stuff to try to transmit a 0 or a 1 to Alice. And in this interferometer, sometimes the decree or the bomb will go off, and that's an error. And in this case, we're going to post-select them away. In the large interferometer I showed before, the fact that we put in many beam splitters made the probability of these errors vanishing small. But let's see how this will work. So we're going to post-select on D1 and D2 ticking. If Bob chooses to remove the bomb, then 2/3 of the wave function will go here. And then this is a balanced Mach-Zehnder interferometer, so that's going to end up at D3. And we're not looking at the D3 outcomes, we're ignoring those. But 1/3 will have gone down here. And then it's going to end up here with 1/6 and there 1/6, but we're post-selecting on these two outcomes. So if the bomb is not there, post-selecting on these two outcomes, you get it here with 50% probability and there with 50% probability. So that's without the bomb. You put the bomb in, these probabilities are going to change. So now 1/3 goes down here. 2/3 go here. And then you have 1/3, 1/3, 1/3. This part gets absorbed by the bomb. And we said that's an error, so we're going to ignore that. So then you kind of collapse, if you like, down to a state where you only have this and this. And then here again, a part of this wave gets now reflected down and part gets transmitted, and the beam splitters are tuned such that this part of the wave function interferes with this part constructively on D1. So if the bomb is present, you always get a tick on D1, post-selected on D1 and D2. So no bomb looks like this, with 50-50 on D1, D2. And with the bomb, you get only D1. So if they repeat it a few times, Alice will be able to guess what the bit Bob wanted to send was. So let's analyze this now. I put in like these conditions, polarization rotations all around this parameter to see where was the particle. And then if you look at output at all of these effectors, that I want to venture out a guess for how much information could you encode at beta 1? This reflects 1/3 and translates 2/3.
1/3.
Mm-hmm. Good. And at beta 2?
2/3.
Yeah. Now theta 3, slightly trickier. Zero. Okay. So why is that? Well, it's a bit tricky to think about these kind of logical way, but like the wave function coming through here goes to a balanced Mach-Zehnder interferometer, and all of that should come out with D3. So everything that comes in here will go out there. And then you could look at theta 4 and theta 5. And they will have a third each. And that's kind of the 2/3 part here being split by this 50-50 and becoming a third and a third. Now let's post-select. So this is what we did when we used this for counterfactual-communication. We post-selected on outcomes D1 and D2. So if the vector D3 takes, we're going to ignore that. In other words, Alice just sits down here. How much information can she get from all of these rotations? So again, how much do you think she'll get from theta 1? Yeah, 1 unit. So why is that? Anything that goes up here will go through the balanced Mach-Zehnder interferometer D3, and we're ignoring those outcomes. So that's the same as saying we're only kind of, it's not quite, but it's almost the same as saying we're only going to look at stuff that's went down here. We look at theta 2. Now that's equal to 0 because everything that comes in will go to D3. Theta 3 is still equal to 0. And now how much will be present at theta 4 and theta 5?
One and one.
1 and 1. Good. So if you do like that with the weight value and you kind of map out according to this kind of information viewpoint, where could information have been encoded into these particles, you get a trace that looks like this. So it's like kind of a discontinuous jump. So if we go back to the original question, then did Bob manage to send a message to Alice without having the particle in this lab? If you think that the particle was present where information was encoded in it, then the answer is no, because information was encoded in the particle in Bob's lab. I have a bunch of other slides, but I think I think I'm going to skip that. The final thing I should say is that Arvidsson-Vaidman had a modification of the interferometer that I looked at that actually gets rid of this stuff in Bob's laboratory and post-selected on the lower detectors thinking. So the universe is conspiring to end this presentation. More happened here. Okay. So just where's my thank you slide? Okay, conclusion. So I think I only got here. So interaction-free communication kind of told for us it's a communication protocol that thanks to build on the Elitzur-Vaidman bomb tester. I've told you that I have devices measured for where a particle has been present based on information-theoretic approaches, and it seems that at least in some scenarios, it can be useful to look at things. I think that things is way too complicated for any kind of educational purpose. So I think it's very operational in that you don't need to consider any extra apparatus in interferometers. You don't need to do anything. You're just mathematically looking where was information encoded in the particle and saying that the particle was where information was encoded in. And then, according to this definition, the older interferometers that looked at counterfactual-communication, they don't achieve their goal with having no particles involved. Laboratory, I think the interferometer of Levs and Yakir's that I didn't get to, it's closer to achieving that. And with that, I just want to say thank you. So the Mach experiment we did, myself with Yorati in Vienna into the Walters group, and then we were using one of their inbox nanophotonic processors to do kind of a concatenated Mach-Zehnder interferometer to have Yorati propose her boyfriend in an interaction-free way. And I think this experiment was the first one ever to do an interaction-free measurement on a nanophotonic processor, and I think it also the first time ever for someone to propose to her boyfriend with interaction-free measurement.
So hopefully there will be more interactions after this.
He said yes. Happy to leave.
Okay, we have a little bit of time for questions. Any questions, Let's
We'll go back a couple slides to the island particle, the ghost particle. Yes, that. So I would say that the notion of where a particle is, the location of the particle, should have some sense of the fact that the particles aren't popping into existence. In this case, they actually think about an electron doing this to an electron, so I feel like it has to have persistence. And so I'm disturbed by having particles inside an interferometer but never having gone into the interferometer or moving the interferometer. That just disturbed me to the extent that I want to just throw this away because it's coming up with things that are not matching what I really want for a definition of the position of a particle.
Well, it's not very scientific, right? Like you should go in and say, this is what I want, and I'm going to throw away anything that's not that.
But also you sort of drop to the side, right? Relative to just the weak values of the projection operators, you get as much information from a negative particle as from a positive particle. If you retain that sign, and as you know, there are no particles in the interferometer, but there are particles in what are the interferometer.
This is Yakir's equation. From my point of view, it's all the negative, positive, there is a trace. If there is a trace, the particle will there. And I think, if you look on a wave function forward, it's kind of coming in. But we consider pre and post-selected particles, so we shouldn't forget the post-selected one. If we look at the wave function of the post-selected one, it is not present in these two places where they are not there, because one of the wave function missing. In the first part, it's backward, in the second part, it's forward. And the particle, the pre and post-selected particle is natural. If you look at pre and post-selected particles, information you get for pre and post-selected particles, not for every, not just for pre-selected particles. So it's natural to say that it's not. That's all. It's a.
Just turn to back people. Like, if you sit here and you know that the particles come from over there, and you just look at your measurement data, you will learn, all these, you will learn, theta 4, theta 5, and theta 1. So if you say that, you're not happy with this discontinuous jump and you don't deal with it, where did the information come from? Doesn't it?
Yeah, I think this is related to your question right now. But I wanted to clarify that this Fisher information is defined with a derivative with respect to the parameter. So
Yes.
if you're setting the parameter to 0, what it's actually asking is if I make a very small perturbation of the parameter linearly, right around 0, can I see that perturbation later on? But quadratic terms are dropped because it's only looking at the first order derivative. So according to the Fisher information definition, it's asking, is there a first order trace left on the particle from the detector? So this is the dual of Lev's trace. Lev is asking, is there a first order trace left in the detector from the particle? You're asking, is there a first order trace left in the particle from the detector?
Yeah.
Of course, these two things should match up because interactions are symmetric. So I'd expect this to give exactly the same results as Lev's first order trace criterion.
So this is the physical review paper.
Yeah, so maybe we should write that up.
Yeah,
No,
sure.
it's
But I don't know.
So there is,
In terms of Fisher information.
yes, okay. But I had to admit I hate it, but I had to do this.
Well, you hate to do sophisticated method in your own papers.
But I'll follow that up with Ephraim's comment. Is this trace criterion ignored the sign, which is there in the lead value. So that may also be relevant, but it's not in this definition. Because he's squaring.
And the absolute value is there in the definition of the Fisher.
Exactly. He's squaring away.
Yeah, so I'm really puzzled that Fisher information may not be the proper measure for the computation. But I would consider it would be the key rate essentially. Because
Which one?
key rate. Because if you go to the case that when you exceed the one limit that you have, I mean you had a problem. Yeah, so I can tell you. So you can exceed 1, I mean, even you can go to 10 or whatever. But the problem is that how frequent this is happening. How many photons are you sending? And what are the probability? So essentially, you have to go with information perceived or per carrier, essentially. Yeah, exactly. That's that one. So I would say that maybe the key rate would be the proper measure, which essentially you should consider that the Fisher information. Because that's based on the postulation, right?
Well, yeah, I mean, these measures would match up if you were looking at both the detector outcomes, but if you postulate, if Alison is here, this is the key rate. This is the rate of information transmission that she receives per photon.
Per photon that is going to the system or per photon that is detected?
Per photon that she detects.
Well, that's not a proper measure.
I think that's,
I mean, Fisher information normally is saying, given a photon coming into a box, what's the most that you could extract information you could extract from it?
So I mean, like I can answer this question in two ways. One thing is just like, if you sit here and you want to know how sensitive are your particles to change this, this is the measure you get. But then if you want to be more operational, I think, but I want to extract information from these states. You could say, like, you're not winning any information by doing this because you're trying to extract stuff, but things will be end up here very rarely. But under these papers from Justin and Andrew Jordan, can say that maybe by other people in the room as well, that by Ephraim, myself, maybe. Say that you have a single, just like say that you have a single photon, so you can use 1,000 particles per microsecond. But your detector can only detect 1 particle per microsecond. I think the best single photon source can produce single photons 1,000 times faster than the best single photon. So now what you do, you try to go back to the benchmarking thing at the very beginning here. So I want to measure this polarization rotation. I will put my laser here, and I will start pumping it. But if the intensity of the laser is 1,000 times stronger than what your detector can deal with, you will saturate and you will be sad. You're not going to learn anything. So what you could do then is to put a filter there that blocks out 999 photons. And you're not going to saturate your detector, and you're going to learn the value of theta at 1,000 of the rates that you could have if you had amazing detectors. Or you could do what Ephraim and his grad students did in this recent experiment we had out. It's not quite this, but you put your detector here. And then you put your laser here and you pump it at its full power. You tune the speed splitter so that it only lets through 1 in 1,000 photons here. That 1 in 1,000 photon will carry the full Fisher information of all the particles that were here. So in this scenario, when you have a detector that can saturate, you can use this kind of post-action or filtering in order to compress all the methodological information to a few. And if you do this, you're going to learn at a rate, I think, in Ephraim's paper, 200 times faster than you could if you didn't put a post-action filter.
This is also what they do at LIGO as well, right? They balance their system based on the dark fringe. But they're extracting all of the information of the entire interferometer, even though they're only measuring just a small fraction.
Yes, it's in fact what's happening. So you're doing interferometer in the dark fringe. And then in the dark fringe, if your detector is just operating at optimal intensity for small fluctuations there, then you get all the information and fluctuations on the dark fringe.
Yeah, we'll have one more exchange.
So
I want to make sure Abby gets to
the same story can be said in the weak values because we have projection, weak value projection much higher. But I prefer the weak local trace than this story because if you go to this nested interferometer, then in one case your Fisher information can be lying. Because if Andrew is not here, but if you put a Dove prism inside inner interferometer, or if you have this polarization, some device which flips polarization, then I will say that it will give me wrong claim about where was the photon. Because the photon was not there, but if you put in the first thing.
You want to put something here?
Now, I will put a Dove prism right here. Then there, it will be sensitive to what is there, in spite of the fact that from my point of view, the photon as the particle is still not there. So it will be wrong. The photon will be lying. This is a kind of series of papers when everyone.
So if you put a Dove prism here.
Yes. Then you will be sensitive to a detector. Put back your detector. The theta. The theta stories. The theta stories inside this. Yeah, theta 2. If you put device inside inner interferometer, what it does when it's kind of zero, it does nothing. Yeah. But then it's go to the left, it's flipped to the right. Yeah. Only in one arm. Then now theta 2 will work like theta 1 or even twice theta 1.
Yes.
Which is but it will be lying because the photon still will not be there.
No, I mean if you put the Dove prism here,
yes.
when you function from theta 2, it's going to reach the
No. It's still not nothing.
This is wrong.
You put the Dove prism and you compensate the phase and whatever, it will work the same, still with the tunes to this way. You put a dove prism and tune to these three. You can do this. But now it's sensitive to temperature.
Yeah, I think we should conclude the discussion here. You could continue debating this later. Let's thank David and all the speakers today.